So negatives modulo, so I don't know, let's do negative 20 mod 7. Right, so you want to write negative 20 equals something times 7 plus some remainder, right? This is the remainder that you're looking for. So could be negative 3 times 7 is negative 21 plus 1. Right, so this should be congruent to 1. The way that I usually do it is negative 20, just add 7, gets me to negative 13, add 7 gets me to negative 6, add 7 gets me to positive 1. And you can do that the other direction if you want to know what 15 is, mod 6. Right, I can do 15, subtract 6, I get 9, subtract 6, I get 3. 3 is the answer. So you can keep adding or subtracting this moduli until you get something between 0 and moduli minus 1.
And the last same question, the number of bit number of
yeah.
How to
Oh.
When you multiply it out, it ended in 0.
I know the fraction.
Use like a calculator and multiply it out.
Right, whatever it happens to be. Remember, the whole idea of modular arithmetic is we can work with the original numbers, or we can work with those numbers mod 10 anytime that we want. So what is this congruent to mod 10?
6.
Right, it's just 6. And what is this congruent to mod 10?
2.
It's just a 2. So this is congruent to 6 times 2, which is 12, which is just 2. And that's just a nod to the fact that when you write these out and you do your multiplication, this first digit you write here is always this digit times that digit. It's whatever the low digit is, right? That's why that works, because you're just doing mod 10.
I just multiplied it out. I just multiplied it out. It gave me a 0 at the end, so I was like, all right, that's 0, 1.
Okay. Should have made the numbers bigger. All right, so so PA1 is mostly graded, and PA1 looks good. That is not a wall wash. Come on. Here we go. Yeah. So PA1 is graded. PA1 looked good. A few issues with not terminating strings. If people were storing array element or set elements in strings, sometimes you'd forget a null terminator and then you get lots of weird stuff coming out at the end. A few odd cases with empty sets not being treated exactly as they should be. But by and large it looked really good, and as far as coding to implement set functions and so on, that was all good, so I was happy with that. I posted PA2. And PA2, you're going to play with Goldbach's conjecture. Remember, Goldbach's conjecture says that any even integer can be written as the sum of 2 primes. Okay, so 4 is 2 plus 2, 6 is 3 plus 3, 100 is something plus something, where those somethings are prime. And it claims that you can always do this. So you're going to write a C program to verify this. And I want your C program to ask the user for a starting number and how many numbers to test. So if I say start from 1 million and test 100 numbers, it should test all the even numbers from 1 million up to 1,198. Okay? And you're going to write a program, preferably a function, that tests Goldbach's conjecture on different even numbers. And I'm going to tell you something here that will make your life easier. And if you paid attention when I said that for PA1, you probably had a pretty easy time with PA1. And I saw some PA1s, some of them worked, some of them didn't, but that might have been like 500 lines of code. And probably took quite a few hours to write, and those did not follow my suggestions. Which is okay, you don't have to do it my way, but if you want to save yourself some trouble, I'll give you a suggestion that will help. Okay? So here's my suggestion. You're trying to tell whether or not an even number can be written as a sum of 2 primes. So make yourself a function, okay? Test n. See if n equals sum of two primes. Thanks. Okay, some kind of function that just takes one even number, tries to write it as a sum of two primes. And then your main program deals with printing something for the user, getting their input, all the scanf nonsense, that kind of stuff, and then goes in the loop and just keeps calling this test function. Okay, but modularize the heck out of this. It will make your life easier. So how do we test to see if n can be written as a sum of two primes? Okay, there's a really, really, really slow way to do this. And if you do it this way, your program will not finish. So I don't recommend doing it this way. Your friends will be like graduated and working at companies, making money. You'll be waiting for PA2 to run. So don't do that. So don't do this. For p equals 1 to n, for q equals 1 to n, if p plus q equals n, if p is prime, if q is prime, print p plus q, right? Otherwise, go back and keep looping, okay? If n is 1,000,000, this is going to run 1,000,000 times 1,000,000 times. That's 1,000,000,000,000 times, okay? Fast CPU, not going to take 1,000,000,000,000 iterations well. It's going to run forever, okay? You're doing way too much work like this. So an easier way would be something like this. For let's call it, for p equals 3 to n. You only have to go up to n over 2. Okay, so for p equals 3 to n over 2, if p is prime, q equals n minus p. If q is prime, then you're done. You know that your number is equal to p plus q. So we're only testing our first number if it's prime, and we're not testing every other number to see if that number plus p equals n, right? We're subtracting p from n and saying, is that difference prime? And if it is, then we know that n plus p is equal to q. Okay, make this a little nicer. Throw that in the bit bucket. Okay, make yourself an is prime function. Takes an integer, tells you if it's prime or not. So if p is prime, q equals n minus p. If q is prime, then you found a way to express n as a sum of two primes. So print out p plus q equals, whatever n is, right? So generate that output. I don't have sample output here, but I say it's somewhere in the words. So if you're testing 1,000,000, you want to print out blah plus blah equals 1,000,000, right?
You want it in a PDF file, though.
Ultimately, I want it in a PDF, yeah. I'll tell you how to do that in a sec. Okay, so if this is true, print this and then just return.
And if it's false?
And if it's false, then just go back to the top of your loop. So you got a single loop here. Your first loop is going through all the odd numbers up to, and again, you only have to go to n over 2.
Is that first loop incrementing p?
Yes, for p equals 3 to n over 2. See if
Can
p
you
is
go even
prime.
less than that?
Say what?
Can you go even less than n divided by 2?
Not really, because it could be that n over 2 is the unique prime that added to itself gives you n. So it's not like square roots when we're testing. And since we know Goldbach's conjecture is true up to 1,000,000, right, and way beyond that, we could make this a forever loop, and we know that eventually it's going to find a solution. But to really do this cleanly, right, go up to the largest possible candidate, make sure it's prime. If it is, see what the difference is, see if that's prime. If you come out of here, you found an exception to Goldbach's conjecture. You found an even number that cannot be written as the sum of two primes. Okay, so here we can say return 1, saying we succeeded. here we could return 0. So this is our test function. Takes an integer n, returns a flag. So your main program, check the return from test. If it's a 0, either you did something wrong or you found a number that can't be written in this way, which is fame and glory.
Or bug.
Yeah. All right, does that make sense? Okay, this will take on the order of 1,000,000 steps. The other way will take on the order of 1,000,000,000,000 steps. Okay, and it just won't finish. All right, so write your code, test it, make sure it all works, and then do the following: cat, mycode.c. That gives you a printout of your code. Run your code, tell it you want 1,000,000 and you want 198 numbers or whatever, and you get all this output on your screen, right? Okay, grab all of that, copy it, go into your favorite text editor, Word, LibreOffice, whatever, paste it, save that, export it as a PDF, and then upload the PDF to Canvas. So when I look at the PDF, it should have your source code and it should have the output from running your program. It's got to have both pieces.
Like we're emailing you a question.
Say what?
Like we're emailing you a question.
Yeah, exactly. Okay, I'm not worried about format, font, if you have the source code first or last or anything like that, but I need to be able to see the source code and I need to be able to see the output. Okay, this means you can write your code in C, you can also write it in C++. That's fine. But you have to write your own code for testing primality. Okay, don't write this and use a library that has an isPrime function for you. I want to see the code that actually tests to see if a number is prime. And to test if a number is prime, you can go back to your 121 notes, okay, or ask questions about it. Basically, you divide by consecutive odd numbers starting at 3, and there you only have to go up to the square root of the number. And that'll save you a lot of time, because for 1,000,000, if you go all the way up to 1,000,000, that's 1,000,000 operations. If you go to the square root, it's 1,000. So it's about 1,000 times faster if you only go to the square root. So 1,000,000,000 times faster if you take both of those pieces of advice. All right, make sense? Cool. Any of your friends who aren't here right now, if they get stuck and their program's taking 1,000,000,000 times longer than yours, you can be nice and point them to the lecture or give them some advice. Or ask them to post on Canvas. All right, we got a half hour. Let's talk about RSA. So we were talking about crypto systems on Wednesday. And I made the observation that most crypto systems, the way that you encrypt and the way that you decrypt are related to each other. In a shift cipher, if you encrypt by adding 5, you decrypt by subtracting 5. If a transposition cipher, if you move these things around like this to encrypt, you move them back the other way to decrypt. And so there's this relationship between them. So that changed partially on account of these three people. So Ralph Merkle is the person on the left. I actually met him in the late 90s. He's doing some really interesting stuff in nanotechnology. Martin Hellman is in the middle, and Whitfield Diffie is on the right. And there's a magnetic tape in the background right here. There's one of the spindles. And mostly we didn't have CRTs back here, so everything was printed out on paper, which was kind of cool because you always had a hard copy of what you were doing, but it wasted a lot of paper. But it gave you something to take home or take to the bar and look at with your friends. So Martin Hellman was at Stanford, and he started having this idea of, could it be possible to develop a crypto system that used a different key for encoding and decoding in such a way that if you knew how to encrypt, you could not decrypt, right? And he wanted this to happen because he figured out if you could do this, you could do secure transactions electronically over some kind of network. Networks were very early stage at this point. And he talked to people about this, and they told him that's impossible, right? If you know how to encrypt, obviously you know how to decrypt, right? But he had this feeling that there was a way to do this, and so he he set about trying to figure out an algorithm. So Diffie, over there on the right, he got his bachelor's in math from MIT in 1965, and he started traveling around the country looking for crypto researchers, kind of interested in similar notions. And he got to IBM, and someone at IBM mentioned Hellman to him and said, you should go talk to this guy. So he contacted Hellman, and he made an appointment for a 30-minute conversation sometime early afternoon, I think. And he showed up at his door, and they started talking, and they talked, and they talked, and they talked, and it got to be dinner time, and they got some dinner, and they kept talking, and he left about 11 p.m. that night. It was just like they were both on the same wavelength of these ideas about crypto systems. So they started doing some collaboration on this idea of asymmetric key ciphers. Now, Ralph Merkle was an undergrad. He was at Berkeley, so north of Stanford. And he was taking a computer science security class, and they had to pick a project, kind of like a 1/4 SLP project. They had to pick a project, and he thought it would be cool to do a project with asymmetric key cipher. So he wrote this up, and he gave it to his professor. And the professor said, quote, your project is terribly muddled. And he said, no, you can't do this, right? This isn't well enough defined. And so like any good computer science student, his reaction was to drop the class. And he spent his time working on this project on his own instead. And he thought it would be fun for like, a 1/4 project. So mid-70s, he was working on his master's degree at Berkeley. And he was still talking about this stuff. And somebody heard him talking and said, there's a couple of guys up at Stanford who talk a lot like you. And so he went up to Stanford, and he found Hellman, and he became his doctoral student. So the three of them were working together on this idea. So shortly after that, Hellman published a paper. And in this paper, it basically laid the mathematical foundation that we're going to go through in a minute for doing this idea of a public key cipher. And it was a cipher that was extremely secure and extremely difficult to crack. Right? It could let people send information securely without having to exchange some kind of secret encryption key. I could say, hey, here's my key. Anybody who wants to send me information, use this to code your message. And now everybody, right, I could post that on my emails, I could tattoo it on my forehead, and anybody who saw it could send me secure messages, but they wouldn't be able to decrypt what messages were being sent. Only I could do that. This is a huge security issue for the government. Right? Because government likes being able to keep secrets. They don't like other people being able to keep secrets. Right? So NSA, they're all about how can we figure out what other people's secrets are while keeping ours safe. So some of Hellman's colleagues got worried about this. What are the implications of having this kind of secure communication that our government can't decode? So one of his colleagues contacted NSA, National Security Agency, or no such agency. And NSA looked into it, and they classified this algorithm as a munition. It's an instrument of war. And once something is classified as an instrument of war, there's all kinds of restrictions on what you can do with that, including exporting it or giving it to somebody else. Well, these people were researchers. They were going to publish their results in a journal, and that journal would be available across the planet. Well, technically, that's exporting an instrument of war. That's a huge crime, okay? It's like building a bioweapon. And so the government said you can't do that, right? That's a felony. So Hellman planned to present this at a conference anyway in October 1977. And he talked to the legal people at Stanford, and they basically said, if you're prosecuted, we'll defend you free of charge. Okay? If you're convicted, we can't pay your fines, and we obviously can't go to jail instead of you. And, he was a tenured professor and pretty established in the career, and he wanted to go ahead and present this paper. His grad students also wanted to present the paper, and the advice to them was, don't do this, right? You're not employees of the university, so you don't have the same protections that your advisor does. You're also very early in your career, and you don't want your first paper to be followed by a felony jail sentence of 25 years. It's not going to work well for you. They planned to go ahead and present anyway, and then they talked to their families, and their families talked them out of it, actually. So at the conference, which was in Cornell, Hellman went up on stage, and he was presenting work from the students. The students were on stage, but they were off on the side. And nobody knew what was going to happen. It was really tense, because they didn't know if the government was going to show up and storm the stage. Were they going to arrest these people? Was something worse going to happen? In the end, nothing happened. They presented the results. The government did not step in, and that was it. The cat was out of the bag. And once this was disclosed publicly, right, everybody knew about it. So public key cryptography became a system that was basically the end of the government monopoly on secure encryption. So that was mid-70s, not that long ago. Anybody here remember Netscape? Apparently. So Netscape was a browser before, you know, Chrome and Explorer and all that. And there were two versions of Netscape you could download. If you were in the US and you promised to play nicely, you could download the secure version. And if you didn't sign that agreement, or if you were outside the US, you could download the less secure version. It was different encryption systems that they used, one that the government felt they could crack and the other one that they felt would be harder. So security now, I mean, we just kind of assume that we can encrypt our stuff and we're not going to go to jail for it, but that's a relatively new phenomenon. When this was first coming out, 70s, 80s, it was all kind of a bit of the Wild West. All right, so let's look at this public key system. So this is something called RSA.
Is AES close to it, or?
I don't think AES is public key. I think AES is a symmetric cipher. So I think the same thing for encrypting and decrypting works both ways, kind of like DES. But AES is much more secure than DES. DES was...
Is it just because it's harder to, it's just much more jumbled?
Yeah, I think it's more jumbled, and I think it's a bigger search space for the password. So RSA initials are the three people who came up with this. All right, so here's how we do our encryption. We start off with two large primes, so pick P and Q, very large primes. Really large, okay? And set N equal to their product. And then pick an E such that the greatest common divisor of E and P minus 1 times Q minus 1 is equal to 1. In other words, E is relatively prime to P minus 1 times Q minus 1. All right, so the public key, which we use for encrypting, is this pair N comma E. Okay, so I'm going to tell the world, when you want to send me a message using RSA, here's my value of N, here's my value of E. The secret part are the primes P and Q. So if I tell them N is 35, that's not very secure, because they can pretty quickly figure out P and Q are 7 and 5, right? Because those are the two primes that multiply to 35. So you want your P and Q to be large enough that if I tell you what their product is, you can't reverse that and figure out what those individual primes were.
At least not easily.
Not easily. So if this is a 500-digit product, the two primes are hopefully around 250 digits each, right? And we don't have a table of primes that big.
That's why they like that 28 million digit prime number.
Yeah, yeah. Except everyone knows that one now. So this is the whole key to why this is secure, because it's easy to multiply P and Q to get N. It's very hard from N to get back to P and Q. When that changes, this is no longer secure, right? Don't buy anything from Amazon that day. Okay, and this is why quantum computing gets people so excited, because quantum computing makes it really easy to factor large numbers, because you can try all possible primes simultaneously. So for now, this is hard to do.
It uses what you talked about earlier in the section where you said, like, if you can easily solve a giant matrix at the same time. Right?
Similar idea, yeah, yeah.
So it's still, like, it works the same way, because if you can renormalize like a giant matrice and solve it all at the same time, then you can renormalize a giant set of primes, right?
Actually, I wonder if you can do this with matrices. How hard is it to reverse the multiplication of two matrices? I wonder if there's a different way to do this.
I was gonna ask, is this the only way to do like a asymmetrical set?
No, but you need some kind of operation that's easy in one direction, very hard in the other. And mostly we pick on primes, but there's probably other operations that are similarly one directional. Okay, so we're going to work on a simplified set of input, which is just uppercase letters A through Z. Okay, we've seen this before. And I'm going to use 2 digits to represent each letter. So A is going to be 0, 0, B is 0, 1, C is 0, 2, Z is 25. There's nothing magic about this coding, but the idea is I'm going to take a set of input text and translate it into a big long integer. And I want each of these to be 2 digits so that when I look at my big long integer, I can turn that directly back into text. Okay, so I don't want to have some 1 digit, some 2 digit ones. And you could have more numbers, more characters than just 26 and so on, but just for simplicity. So M is your message. And we're going to do this encryption on pieces of your message. So we're going to break your message into blocks. So, so we're going to break into blocks of 2n characters such that the largest possible message we might write, which would be a bunch of z's, right, 2n of these, is still less than n, that product of p and q. So that can get arbitrarily complex, but basically we're taking your message, we're turning it into a bunch of integers strung together side by side, and we're going to work with a block so that the largest possible integer, a bunch of z's, is still smaller than this magic number n. Okay, so if n is the number 1,000,000, we could only have 3 characters, right? But n is really big.
Right? 2 capital N is...
Yeah. All right, so we're going to break your message into these pieces. All right, so M equals a message. And let's assume M is less than N, so it's a piece of that block size. And your encryption key is little n, comma, E. Okay, if you know P and Q, you can find an inverse D such that D times E is congruent to 1 modulo P minus 1 times Q minus 1. We won't go into how to do that, but if you know these primes, you can find an inverse of E such that D times E is congruent to 1. Okay, so how do we encrypt? So our ciphertext is just M raised to the E modulo little n. So someone tells me my encryption key is n comma E. I take my message, right, written as a big long integer, I raise it to the power E, I reduce it modulo n. That's the ciphertext. That's what I put out on the insecure link and I send to this person. And we can do this, modular exponentiation, Fermat's little theorem, something. It's pretty easy to do this. Well, it's pretty easy for a computer to do this. Okay, so the person receives this ciphertext C. How do they decrypt it? So decryption, and this is where we get to use all the good stuff. Okay, so D times E, right, we can find this D. Nobody else can because they don't know the P and Q. So we can find this D. So since DE is congruent to 1, modulo P minus 1 times Q minus 1, So we can write DE as 1 more than some multiple of P minus 1 times Q minus 1. So if I take their ciphertext and I raise it to the power D, I'm going to get, well, the ciphertext is M raised to the E raised to the D. Which law of exponents? This is M raised to the D times E. And D times E is 1 plus some integer times P minus 1 Q minus 1. So this is M raised to the 1 plus K times P minus 1 times Q minus 1. And I'm doing all of this modulo N. So they send me some encrypted text C. I'm going to raise it to the power D, and I'm going to reduce it modulo N. And the claim is that's going to bring me back to my original plain text.
What did you K 1 plus K? What did you do?
So since D is congruent to 1 modulo this, it means D is 1 more than a multiple of this. So it's equal to some multiple of this plus 1. Okay, well, modulo N is also modulo P times Q. So we need to make one observation here, and then we'll make another observation in a minute. If A is congruent to B modulo P times Q, that means A minus B is some multiple of P times Q, which means A minus B is P times some integer, which means A is congruent to B modulo P. So if two things are congruent modulo P times Q, they're also congruent modulo P, and they're also congruent modulo Q. That's just kind of a consequence of divisibility. So since C to the D is congruent to this modulo P times Q, we know the following. C to the D is congruent to M to the 1 plus K times P minus 1 times Q minus 1 modulo P, and also modulo Q. Now, as long as M is not a multiple of P, and it's very unlikely, since P is this big prime and M is a coded message, it's very unlikely M will be a multiple of P. And if it is, we can just, add an extra space at the end or some extra character to make sure it's not. So we can assume M is not a multiple of P. We can use Fermat's little theorem. So what does Fermat's little theorem let us do? Well, C to the D is congruent to, well, this thing is M times M to the K times P minus 1 times Q minus 1, which is M times M to the P minus 1 times K times Q minus 1, which is congruent to M times M to the P minus 1 raised to the K times Q minus 1. And this is mod P. Well, M to the P minus 1 modulo P, Fermat's little theorem tells us that's equal to 1. So this is congruent to M times 1 raised to the K times Q minus 1, which is just congruent to M. And we can repeat this whole process and show that C to the D is congruent to M modulo Q.
So if we just mod Q, C to the D, we'll get
You'd get M, but Q is potentially smaller than M, and P is also potentially smaller than M. But the other fact we can use, we got time to be careful with this. If A is congruent to B mod P, and A is congruent to B mod Q, there's something called the Chinese remainder theorem, which we haven't talked about. But one consequence of the Chinese remainder theorem is this: if A is congruent to B mod P and also mod Q, then A is congruent to B modulo P times Q. Assuming P and Q are prime and not equal to each other. And this is actually pretty easy to see, because if A is congruent to B mod P, this means A minus B equals P times something, and also A minus B equals Q times something. Well, we know we can write A minus B as a product of primes, and that product is unique, other than the order of these primes. Well, this tells us at least one of those primes has to be P, and this tells us at least one of those primes has to be Q, because P and Q are both prime. So A minus B will be something times at least some P times something times at least some Q, which means it's PQ times all the other factors. So this particular consequence of the Chinese remainder theorem we get just from unique factorization of primes. So this is congruent to M mod P and also mod Q. Therefore, C to the D is congruent to M modulo N. And remember, our block size was chosen so that the largest possible message M is smaller than N. So if we take the ciphertext, raise it to the power D, reduce it modulo N, we get back the original message.
We just get a bunch of digits, and then we...
Bunch of digits, and you just take each two of them and translate it into a character. And there's your original text.
And then that's even if you do another symmetric cipher on top of that.
Yeah. All right, so this works, and it uses GCDs, it uses Fermat's little theorem, it uses Chinese remainder theorem, and some facts about modular arithmetic. I don't know how someone came up with this, and I don't know what the exact proof is that finding this D is difficult if you don't know P and Q. Right, but presumably it's hard to do just from knowing the product of P and Q.
Is it more difficult than trying to solve for P and Q?
Yeah, presumably. Oh, actually, I don't know. It should be on the order of difficulty, but I don't know for sure. It's a good question.
Like, is it worth it to try and search for P and Q, or to just try and
Yeah.
find D?
Interesting. And I think D is going to be bigger, but I don't know. I don't know what kind of attacks there are against this. There's definitely some.
What about the point you made where, like, bigger primes are more useful, and we just have a list of all primes? Like, it feels like you said, you're not going to use 35. That's pretty
Right.
easy to figure out. So, I mean, through just kind of that sideways thinking, it feels like this actually wouldn't be super secure, but it's used, so.
Yeah, so I mean, you could start at some arbitrary number and then brute force look for the next prime after that. So if you want a 30-digit prime, you could just start with some number with 30 digits, maybe randomly generate it.
Isn't there a database with all the primes up
Yeah.
to like 100+ digits?
No, I don't think with all of them. There's isolated primes we know that have lots of digits, but I don't know what the largest database of primes is. That's just the largest known primes, but largest database of all consecutive primes up to some point, that I don't know.
Well, I mean, the thought is we have this, like, order of complexity idea, and we start throwing primes into there until the order of complexity is larger than what we can brute force in a, like, relatively okay amount of time.
Mm-hmm.
And then as soon as we find that cutoff point, wouldn't that basically be, like, primes people wouldn't want to use, at least for one of them?
For one of them, yeah. So I could think up an arbitrary large number and then find two primes beyond that, right? And unless you know what that large number was that I started with, you'd have no chance of really kind of finding
But a
those
database of
primes.
like every possible prime up to the largest current known prime.
They've managed.
Yeah, that doesn't
consecutive.
exist.
But
In
if it
2000
did, that'd be like
Yeah.
really dangerous.
In 2005, we have managed to archive the first 100 million prime numbers.
Yeah, so that's nothing.
They know that there's missing prime numbers. There's research grants, you can find some of the ones that are in the gaps that they know where they are.
So what's the largest chunk they have without gaps?
I don't know, but if you found
So
one.
it sounds like 100 million in 2005.
If you found one of those missing prime numbers, it might be in here
Says
because they're not
first
telling
billion.
anyone.
Yes.
And then use it.
Oh, well, this is classic, right? So
Our
this,
database is now more than double the size, 300 million right now.
yeah.
Well, 2009.
So 100 million primes, so log n equals 100 million. That's not terribly big.
They
of
made it to
n.
1 billion prime
And then
numbers, but that's not
isn't
complete.
there like equations where you plug in numbers and it'll generate a prime?
No, we don't have those yet. You get some that work for a while, but they all seem to break down eventually. If you had something like that, you could start doing some pretty bad attacks.
Yeah, you could just throw in some massive numbers into the variables and get a new prime.
Yeah, yeah.
You wouldn't know where it is, like if it's like what number it is, but
Mhm.
you know for a fact it's a prime.
Right,
And you
right.
could just get two of those.
Yeah. And so this also applies to things like Bitcoin mining, right, or any of these e-currencies. The security of those is built around similar ideas. Easier to multiply than to factor.
I thought Bitcoin used the SHA-256 or was it?
But I think that's based on primes, isn't it?
I'm not sure.
So when you do Bitcoin mining, you're plowing through random sections of search space looking for numbers with particular characteristics. And the reason that Bitcoin has bottomed out is because it's getting harder and harder to find those nuggets.
Yeah.
Right, it's really a
I think
mining
you're
question.
Supposed to like find, you're supposed to like generate a hash with an arbitrary set of numbers at the end of it or something like
Mm-hmm,
that.
yeah,
So like you have to sit there and try combinations and make it a hash that's
Right.
a certain thing.
I had
And it-
torrents for the first million and first billion prime numbers.
nice.
So if you just wanted the first billion prime numbers, you can torrent it.
Yeah, so if you want primes that have 20 digits, right, that's like 1 trillion times larger. And it's unlikely we're gonna get there anytime soon unless we find a formula you can just turn the crank and primes pop out.
Ethereum bounty contracts.
That's another e-currency.
First contract is a competition for the correct solution to, is it a squared or a
I
cubed?
think it's a cube.
A cubed plus b cubed plus c cubed
Equals 33,
So
there
you
you
find
go.
an unfound solution to that.
Yeah,
They don't have any solution to that, that's the point. First contract is a competition for the correct solution. And I assume since it's cubed, the negatives are allowed, so you can subtract and all that.
yeah, but probably not, yeah.
Not
probably not zeros.
realistically possible, probably.
Well, you never know. This one's running on Amazon. So yeah, so this gets into interesting areas. All right, so Monday I will talk really briefly about two other applications of some of this stuff, UPC codes and ISBNs, and then we're going to start talking about counting. So we'll play with counting and probabilities and statistics that come out of that, and we'll do that for the bulk of next week. All right, so I posted homework for next week. That's also related to counting. It's due on Friday, so we'll have two classes before you need to go on your own on that.